right? This will be V1 into Y1, V2 into V, etc., etc. When the currents can be zero, then the, of course, branch currents are very rare. You can write it as Y primitive into VPR. What did we call that? Okay, I'm sorry. This is only for place. I think that's dash. I'm sorry. Is equal to, this is a scalar equation minus IS. This is a matrix. This is a 7 by 1. VBR is only for this. Let us say IBR is only. This is for this one branch. Dash for one element. This is for all the elements. If you write down all the equations and write it in a matrix form, then no equation is coupled to other equation. Right? There are 7 equations. No equation is coupled to other equations. So you will get a matrix. If you want to express it as a matrix equation, this could be a diagonal matrix. And primitive impedance matrix, where each element corresponds to the admittance of the branch. Given branch, basically you are collecting the network parameter information. There's the parameter information here and the source information. If there's a voltage source, you can always convert it to a current source and again. Or you can continue like that, you can change the definition there. Both approaches are possible. You can look at books like now if you consider this equation, I branch will substitute from Y primitive into B branch. B branch will be A into B bus. Mistake here. Into B bus, you can substitute, is equal to I bus. A into B bus is BPR. A transpose by primitive. It just calls for, I think you pre-multiply this equation by A transpose and substitute for VBR from here. You get the equation. A transpose IS would be IS. That's fine. Essentially, you pre-multiply this by A transpose and then you will get the basic nodal equation, where this is your Y bus. derivation you can see anywhere. What I am trying to tell you is, okay, you have to convince students that this is essentially what they have been doing, but a slight modification of the way things are looked at, it gives you a new expression and it gives you a systematic. The next issue is, we said y primitive, okay. Now how to calculate this is in expression. How to calculate the quantity A transpose y primitive A. If y primitive is actually a diagonal matrix, which is true if there is no coupling, then you can write the y norm like this. You can even write an algorithm to this extent. If you know which element is connected where, it's not difficult. The difficulty comes when y primitive has, or when the elements are coupled, then this matrix, that means branch current of any one element, would also depend on the voltage of some other element. So that gets actually reflected in this matrix having some off diagonal elements. That means all the branch equations will no longer be independent of one another. Whichever is mutually coupled, there will be some mutual coupling. That will be a data item. You don't have to really worry. People will tell you branch A is mutually coupled with branch B, or branch B is mutually coupled with branch C, and what's the mutual impedance or admittance. That information will be given. So that's a data. That's a network parameter information. So from there, you can actually create this matrix, write it down. You decide an order for your branches, then that equation comes through. Except that the matrix will not be diagonal. Then it will be not possible for us to write this by expression. If you ask your students to write the node equations by putting coupling between, let us say, this branch, and also some other branch here, not many in the class will be able to write. You can have any amount of, but this method of doing this, I don't have to worry. As long as you write down your A matrix properly and create your y primitive properly, you are guaranteed of an error-free answer. Even though the formulation looks very compact, right? Computationally, it's actually not very efficient. This matrix is a P by B matrix. This is a N by B, and this is a B by N. It's a huge matrices, right? Even if you want to multiply that, it takes a lot of effort. So, even though it's nice to show that it's what's the basis, for implementing you need other methods. So now, for elements or circuits like that, if I have the branch information, if you know the branch number from and to and value, if this list can be created in a computer. So from here, finding this matrix is easy. So take any branch, right? If it's, let's say between nodes P and Q, it has a value y, then you go to row y, in the location ypq, you put a minus ypq, on the diagonal ypp, you put a value ypq. Each element contributes only to 4 places. That's what you have to see. You see let's say YAB. YAB is actually in row A, row B, and where on the diagonal element and the off diagonal. Or any element you see, CO, you will see that in element, I did not write it for node O, or you consider CD. CD is here, YCD, minus YCD, YCD, YCD. So, writing the node equations for circuits with no mutual coupling is straightforward. So, take the branch list, each element add it to 4 locations. If it is, the element is between nodes P and Q, add it to the diagonal element P, add it to diagonal element Q, and put a minus 5 in Q at the location Q and Q. But if there is a mutual coupling between elements, then the life will not be that easy. Then we will have to multiply. Many books just use this method. So the paper that I have circulated is a method by which you will be able to find the Y bus even from networks with mutual coupling with the same effort as this. Right? You won't see it in any book yet. So, the paper that I have circulated gives you a basis by which, even for networks with mutual couplings, you find Y primitive and take each element of Y primitive and it gives you the locations to which that value has to be simply inserted. If not, it actually there is a simple derivation for the basis, and there is also an example. Just to convince yourself, you can actually do, there is a detailed numerical example. So I will skip this thing. You see, mostly in undergraduate classes we don't teach Y-bus formulation with mutual coupling. But it's not taught because it becomes very complicated. So when you are actually looking at the syllabus, now that there are techniques available to handle it, that can be added. See, the effort involved for both would be almost identical, so it is no different. So you don't have to actually limit yourself to only situations with no mutual coupling. At least if you are, at least you can tell the students, they will know. So it would be easy. That's the Y-bus problem. There are several other issues which we mostly discuss in the postgraduate classes. How to keep these matrices, how to not lose lot of memory and time by doing a lot of unnecessary calculations. So I won't get into that. Any questions so far? Okay, we'll spend some time on the other approach. Emphasize the connection between network theory and the issue why they do everything correctly, but I'm not comfortable. So that the connection between network theory and pairs, whatever the students know and what we teach in post system analysis, is not thought out very clearly. I think that's the job of us, our job to do it in the class, so that students feel comfortable that essentially it's what they already knew and a little more of extension. But if everything is taught as though it's something new with no connection to what they have studied so far, then it becomes difficult to appreciate. That's my belief. Yes, sir.
Real cases are where do you have spiritual content? Because you are saying
Any transmission line. If there is a parallel transmission line, let's say there is a line which starts from substation in Tamil Nadu, and let's say one goes to Salem and one goes to somewhere else in the same direction. Many times what they do is for some 10 miles, 20 miles, both lines are on the same tower. If you go to a major substation, you will see that there are several lines on the same tower, and after some time they actually move away because right of way becomes difficult, and all of them have to start from the substation. So when lines are on the same tower, there is of course mutual coupling. Even lines going to different destinations many times are in very close proximity. Mutual coupling is a fact of life. So mutual coupling is something that we should know how to handle in power system situations.
But why others have not neglected any other general rules without considering waivers?
So when you actually, if the data is available, then you do it, that's all. Essentially for many transient analysis and other things, essentially when you are looking at, you have to do a lot of things. Even for fault analysis, many times data is available. Except that, see what happens is we are sometimes misled by the standard data that's available, item 37 was 15, that's all. That's not necessarily a practical situation. And the 5 was examples that we routinely do in books, they can't bring in all the complexity of real life. And they are essentially there to demonstrate the procedure, provide clarity rather than bring in all the issues involving the practical considerations. I don't know. There is nothing great about that. Essentially, viewing the same expression slightly differently. As a matter of fact, I recently saw the Geiger and Stevenson for a mutual coupling with essentially two elements. He tries to do something of this type, but not beyond two. He also tries to give an equivalent circuit, not very, very comfortable. I saw that recently. I have not seen that. But this actually is an outcome of my class teaching. At some point, and I have been teaching this for years, and one day I suddenly thought, why there is apparently the A transpose by primitive is fairly easy. So, and many times there was patterns. So I just saw whether it can be formalized. So, essentially each element of Y primitive you can put it in 4. That's exactly like this. What we discussed so far is Y bus into B bus is equal to I bus. This is your Y bus formulation, where Y bus we call as A transpose by primitive A. B bus is the voltage of all the buses with respect to a common reference. I bus is the current that's injected to each bus. If actually we wrote it for all the nodes, if we write it excluding one node, I consider calling it a reference bus, then for a n node network, you will have this size will be n minus 1 by n minus 1. That's when you exclude the reference. Exclude the reference is easy. Write all the equations including the reference. Whichever you want to consider as a reference, remove the row and column. Right? If you keep the row and column, that matrix, you can't do anything with that because that's a singular matrix. Sum of all rows would be 0, sum of all columns would be 0. So n by n Y bus would not be useful from the point of view of network analysis. But for our analysis, we actually use the Y bus excluding the reference. And if this is such a matrix, then if I say Y bus inverse, if I remultiply it by Y bus inverse, then I can say that B bus would be Z bus into I bus, where Z bus is Y bus inverse. That's one way of obtaining the Y bus, or obtaining the Z bus. If you have the Y bus, if you can invert it, you have the Z bus. Whether there's mutual or no mutual, there's no issue. If you find the Y bus with mutual, you can find the Z bus with mutual also by inverting the matrix. Okay. The importance of Z bus is widely used in fault analysis. As a matter of fact, as compared to whereas this is a sort of formulation this is almost equal to solving this network. See, there is an inversion involved. So if you have Z bus, if you know the voltage current injected, you get the voltage by simple multiplication. There is no solution needed because the model itself involves a solution. When you are actually trying to model it like this, the network with a Z bus model, it's some sort of modeling network after solving the simultaneous equations. Because this inversion is involved in the formulation of the Z bus. That's the major effort. So if you have got the Z bus, actually from that point of view, if you have the source information, the solution of becomes trivial. Actually, very easy because we have already done the effort. Therefore, we spend a lot of time in formulating Z bus either by inverting or by error. So if you have that information, that's equal to solving the network directly and or keeping the solution readily so that any modified condition you can get the network performance. That's why we are interested in Z bus. There are other issues about Z bus also. Essentially, Z bus, let's say if you look at this equation, I bus or Z bus into I bus equals B bus. So if I just indicate instead of injecting currents everywhere, if I inject a current at one of the buses, that means if I keep all the other ports open in the circuit, then the voltage I get would be the open circuit voltages. So sometimes this correspond or this can also be correspond to open circuit impedance parameters in a more generalized way. Z bus elements are essentially the open circuit impedance parameters of the network. So if you essentially inject a 1 per unit current in one of the nodes, the value that you get, the voltage that you get at all other nodes will essentially give you the Z bus, one column of Z bus. Can you see that? If I bus, Z bus is a matrix. Let's say I bus is 0, 0, 0, 1, 0, 0 somewhere for the, let's say, peak location. So if you multiply what is it that you give, and this Z11, Z2, so you will essentially every time the peak column, whatever, if this is peak position, so this will be Z1P, Z2P, Znp. So if this is the peak column, that's the product of it. That is, actually it gives you an idea of method finding the Y bus. Given a network, if I keep all the other nodes open and inject 1 per unit current through one node, right? Then the voltages that you measure at all nodes, right, would correspond to one column of Z bus, right? As a matter of fact, that's the first principle that we use to actually define or even develop the methods, right? That's, you should appreciate what Z bus really is. So Z bus is essentially this matrix, so that if you can essentially use these ideas of the implication of injection of 1 per unit current, then it will give you a method of finding various columns of the Z bus. Essentially, again, for small networks, solution is easy. You can do it. For large networks, even that may not be easy. But as a principle, it's worth knowing the principle that and that will help us to derive more general methods. Essentially, the most popular method of doing this is in this what we do is we start with the reference node. We actually grow the network element by element. Right? How do we do it? Essentially, I said that the network is a single node to start with, the reference node, then add one element, find the bus, then add one more element whichever is connected to that, modify that by bus. So if I finish all the elements, I have got the Y bus for Z bus for the whole network. So in this process, then I need actually two procedures, right? When I have a network partially built Z bus, right? Then when I bring in a new element, it's possible that a new element, one of the end of this element may be there, one of the nodes. Every element has two ends, right? Of the two ends, if one of them is there in the partial network, one node, then I can connect it there. If both of them are not there, at that point I will not be able to connect it. See, that's another issue. So, only few of the remaining elements can be added to the partial network, and only those which are at least have one of their nodes already part of the partial network. The other alternative is both the ends of the new element that you have not got is already part of the network, then I can bring it, but in the first case the size of the Y bus increases by one. In the other case, size does not increase. That means when both nodes are there, there will be no new node coming in. So that means a new node will be formed. Or addition of a link, no change in size. So there will be increase in size of levels and the network also. So if I have the Z bus of a network, let's say some reference here, 1, 2, let's say P, yeah. Let us say I add an element, a new element, between P and a node Q with a value ZPQ at node Q. This is the first case. This Z bus I already have of size, let us say P by P. Or sorry, N by N. And at the peak node, I am adding an element ZPQ. Q is not a part of the element, part of the existing Z bus. As I said, the idea is I inject a 1 per unit current. So if I can find that column, that means the voltages at all nodes when I inject 1 per unit current, then I have found the Z bus corresponding to this node. So when I inject a 1 per unit current at node Q, what will be the voltage of this? What I should remember is, I know what will be the voltage of this when I inject a 1 per unit current here, because I have calculated the Z bus. So if I inject a 1 per unit current here, that's exactly identical to injecting 1 per unit current here. From the point of view of the network, if I sit on inside the network, whether the current 1 per unit current comes from here or from there into the network doesn't matter. So the voltages of all other nodes would continue to be what they were. Therefore, the original surplus in this case, which was size n by n, and this is the n plus 1 column corresponding to the node Q. So, everywhere from node 1 to